All right, hi everyone. I'm Jacques. I work for Bloomberg, specifically on our storage engineering team. And today we're going to be talking about the experience we've had with applying some cluster-wide quality of service technology on top of Ceph object storage specifically. So, just for some context, we have a bunch of Ceph at Bloomberg. We have several clusters. People were asking earlier. Not sure why that's a bit pixely, but anyways, so they're split largely by environment. So we have like production, dev, staging, etc. Most of them are multi-site. Not all of them. We have some legacy ones that are not. And there are more that are not shown on this picture, but this is just sort of to give you a rough idea. And the reason for that is if we focus just on the primary site of our main production cluster, we're doing upwards of 400 million requests and upwards of 250 terabytes of data transfer every day on average. That's a lot of work for those clusters to be doing, and so we obviously couldn't do that all immediately, all at 9 a.m. in the day. We need to spread that out a bit. We need some QoS to spread it out. We did build our own. When we started this, we looked around and we couldn't find anything that satisfied all of our needs. So we built our own software-defined quality of service stack that we did speak about in the past. There was a talk with this title by two colleagues of mine at CephLCon 2023. That QR code is a link to the video. I promise it's not a rickroll. And so I wholeheartedly encourage you to go and take a look at that if you want some more details. But in building it, there were some things that we were some goals we had, some things we needed to satisfy that set it apart from the solutions that were out there already. In particular, we needed to make sure that we could apply limits to multiple things. We want to limit the rate at which clients can make requests. We also want to limit the rate at which clients or users can transfer data in and out of the cluster. More specifically, on the request side, we want to be able to break down those limits by HTTP verb so that gets and downloads or gets and deletes and posts can be limited separately because they cost different amounts of compute. Yeah, so we needed to build our own thing to satisfy these things, and these are some things we were trying to achieve. Like what are we trying to achieve when we build this as an organization? Well, first of all, we want to make sure that we have a consistent experience for our users. If we say you're going to get 10 megabytes per second down, or whatever the case may be, we would like to make sure that they consistently get 10 megabytes down, and not whatever it happens to be on the day. Slightly more broadly, but from our perspective, we want to make sure that cluster performance is maintained to a good standard. Obviously, if the cluster starts struggling because there's too much going on, then we're going to impact the experience of some of our clients, which is obviously not desirable. And to that end, we needed to make sure that we could provide configurable limits for each user because the use cases for our users varies very widely. There's no way it would be practical for us to provide our smallest users with the capacity that our largest users need, right? So we need to be able to configure that specifically on a per user basis. So what did we build? Well, here's a high-level architecture diagram. This is sort of the flow of data that in the system we've built. So we have some users on the left here, and there's a data path going through to a Ceph cluster on the right. In the middle, we have an HTTP proxy, which is not quite the standard one that you would get off the shelf. We have made some minor modifications to that. For the most part, that's just so that it can output some extra data. That extra data is just sort of, what are users doing? What requests are they making? Who are they? What data are they transferring? And that gets output as it's happening, so we're not just waiting for the end of the request. And that data gets output just in the form of standard logging that goes to a custom syslog server that we built that does normal syslog server things that outputs logs to wherever you want them to be persisted to. But at the same time, while it's doing that and trawling through all of this control data, it's pulling out the information that we're outputting about what users are doing, bashing that up and shipping it off to a centralized Redis instance. You can see, so we have a bunch of these for each RGW. And then there's a sort of centralized version here that stores all of this data, and next to it is the last component, which is a thing we call policy generator that periodically trawls through all this data in Redis, aggregates it for each user across the entire cluster, what have they done? Because these, I was meant to mention earlier, the limits that we need to provide are for the entire cluster, right? There are various ways that we could apply limits for a per instance, on this RGW you can get this throughput of this many requests or whatever. What we're trying to achieve here is this user gets 100 requests a second, or whatever the case may be, regardless of how many machines they're using to send requests, and regardless of how many machines on our side they end up hitting. So we aggregate all of their usage across the whole cluster, and then use that to limit their usage, broadly. And so this policy generator serves to collect all of that aggregated data from Redis, decide on the basis of what that data is, combined with the configuration it has about what users' limits are, what we should do for this user. Have they exceeded? Are they close to their limit? Do we need to slow them down, etc.? And ships that data back up to HA proxy so that it can enforce whatever needs to be enforced. Another thing I should point out is when we say users here, these are specifically internal users. These are other teams at Bloomberg. These are not external customers, which is important because it has some consequences for the trade-offs that we can make when we're designing the system. We can more easily go and talk to them and find out more about their use case. So here are some problems that we encountered. These are some things that we had not quite considered the full extent of in the initial system. And the point of this talk really is just to, we're going to go through some issues we've encountered along the way, and talk about sort of, what we did or are doing to address them, with the idea being that if you are implementing or considering something similar, then, maybe you should think about these things. I don't know if you're on my list, but... So, transfer limit enforcement. Well, here's a graph, right? This is data transfer for a single user in a single direction. The green squiggly line is the actual transfer that they observed. The orange dotted line that is slightly thicker is the limit that we have configured for this user. And you can see, kind of it's sometimes a little bit above and it's a little bit below sometimes. But broadly, it's pretty much the same. If it goes above a little bit for our particular use case, it doesn't really matter as long as they're pretty close. And it is most of the time, but only most of the time. Right? So on this side of the graph, the user is probably over the moon. Their transfers are going super fast. They're happy. They expected it to take 10 seconds. Maybe it took 5, whatever the case may be. But obviously, the flip side of that is our system is now under more strain than we had expected it to be. Which, if a single user is experiencing this, probably isn't the end of the world. The cluster, has some extra capacity on top of it, what it specifically needs probably. But obviously, if this happens to many users concurrently, then that's a problem because the whole system is going to end up taking a bunch of strain and probably slow down. And also, on like a larger time scale, this is a problem because one of the things that we use the limit information for is forecasting the hardware that we need, right? So if we want to know how many RGWs do we need to be running, well, we can take data from benchmarks that we've run on the hardware that we have and like load tests and whatever, combine that with the aggregated usage limits that we've allocated to all of our users and sort of try and use that to okay, how fast are we growing? How many gateways do we need to add to make sure that we can keep up with the demand that we're seeing? And if these two numbers, if reality diverges from the configured limits too far, then those calculations are just not particularly useful, right? Because it's not going to match up to what we actually need.
Once you dock something.
So, clearly there is something that needs to be done about this. And to take a look at what we did, let's refer back to this diagram that we saw earlier. This is the architecture diagram of the system. Here you see the sort of control data path flow for powering this QoS system. And if we just zoom in for a second on this line, we're transmitting some data from policy generator to HA proxy to power the enforcement that we're applying to the user. But what is this meant? What does this line mean if we zoom in here? Well, surprisingly simply, it's just, is this user over their limit, right? The system that we have at the moment is entirely reactive. Until the user exceeds their limit, it does nothing, and then it just, once the information that has propagated through the system to say, you were allowed 10 megabytes per second, you've gone to 11, or whatever the case may be, you need to slow down. We send a message here to say, right, you're over, and HA proxy responds by just suspending entirely the data transfer for that user for the rest of the time slice. Now, our system is defining rate limits on a per second basis. So when I say time slice here, that means for the rest of the second, and because they're still trying to transfer to make sure, and they've already exceeded their limit, to make sure that we kind of stay over or stay kind of at their limit, we also suspend their transfer for a small, semi-random amount of time at the beginning of the next second. And for how simple the system is, it is shockingly effective. This works pretty well, but it has some issues, as we have seen, and so there was something that needed to be done. And keeping the theme of simplicity, we were like, right, well, let's make some single small improvement to this. Let's just add to this message one number, which is how far over the limit is this user. We have this data already because when we aggregate all the usage data in Policy Generator, we know what they've done and what their limit was. So we just do the division and add it to this number. And then we can use that information when we suspend users' transfers to bring them back in line with their policy to just scale how long we suspend their transfers for, right? If they've gone further over their limit, we need to bring them down more quickly to come in line with what they should be using. And this is a definite improvement. This is what we're running in production currently. It works pretty well. It's not fully there because fundamentally the system is still a fully reactive system, right? We still do nothing until a user has exceeded their limit, which means that, sadly, because the speed of light is finite, they exceed their limit. The data to say that still has to traverse around the system before it can get back, and we can slow them down, right? And so the fact that we never preemptively slow them down means we're kind of bound a little bit in how well we can do, and also it means that the users that are going to end up going over their limit further are the users that are going faster, because in the time it takes the message to transfer, they can transfer more data, which is a little bit circular and not ideal. So we have some ongoing experiments to see sort of, what can we do to take a different tack on this problem. Across an entire cluster, we need to limit users to a particular rate limit, and the leading sort of approach at the moment of what we're trying out is let's replace that message of for a single user how far over with instead just, for this HA proxy, this specific one, right, we have many of these, this one, here's a local limit of the user's configured throughput limit. And so to give an example, let's say we have 3 instances and maybe we've decided that there's this kind of split. Policy Generator sends separately to each instance. You get 50% of the configured limit, you get 30, you get 20, whatever the case may be. And we can't just do this statically because then we're requiring users to have a particular usage pattern across our instances. And so the system is dynamic. Maybe the left instance, it finishes up its work and they're still using the other 2, and now we have 60-40, and then maybe the load split between the 2 instances changes, and now we have 50-50. But the point here is that it is doing this on a regular basis, right? Like many times a second, we're recomputing this limit and changing how the HA proxy instances are enforcing things. And that all sounds great, but it is important to note that computing this limit, like, what is this 50%? How do we get to 50%? Doing this is actually surprisingly difficult because it's not at all clear how do we even know, like ahead of time or as it's happening, what we're supposed to allocate, right? Because if we're slowing a user down, well then like we're simultaneously trying to measure and impact the system, which has some weird effects, right? And we have some ideas, as I say, we've got some ongoing experiments, but if we can do this, right? If we can come up with a reasonable way to estimate usage per instance, then we've reduced the problem down to, for like this specific process, you have a rate of data transfer through that process, and you just need to do it for just that process, which is like largely a solved problem. We can do that. It helps actually that recent versions of HA proxy actually have a pretty solid system built in to do this. And because we're modifying HA proxy already anyway, it's pretty low overhead for us we can't quite use it directly, but sort of bend that to our will. So we can rely on the work that project has already done to improve the system that we're applying now to a distributed context. So that was sort of where we're at with trying to enforce transfer limits. Let's now take a look at what happens when you have users trying to set up many concurrent transfers. Right? You have a user. they're running some job. Let us imagine that it is embarrassingly parallel. It's some batch job. They just need to collect a bunch of data. They're talking to your cluster. This is the rest of the cluster under here. They're running it. Their software works fine, but they would like to go faster. And so it's 2024. What they do is they spin up more machines, or they get more hardware, or they use more racks, or whatever the case may be. And now it's faster. If everything parallelizes nicely, you've got more I/O going on, and they're happy. It's faster, but it needs to go even faster. So we spin up more machines, or we use more hardware. Hardware is cheap, right? And let's say at this point we can't use more, but we are smart developers and we added configuration, and so we change a number, deploy, and now all of our instances of software are now making many connections, and all your I/O is very parallelized. And the users, once again, are now super happy. But in keeping with the theme, the cluster is now a little bit less happy because, of course, we have finite capacity to accept and process requests and transfers and connections, right? And we can, of course, scale up like the cluster behind this square. We can add more gateways to distribute the usage across, or we can increase the resource usage on this one or get bigger machines, whatever the case may be. But fundamentally, we're never going to be able to practically keep a cluster that has more hardware than all of our users combined, right? And so we need to make sure that we can enforce some limit here, right? So we can't have users that get too crazy. This fundamentally means that we need to do some form of limiting of connections that clients can open. There isn't a huge amount of options here. We can either, if you have a hard limit on the number of connections that a particular user is allowed to open, your options are basically interrupt existing ones if they try and go over that, or prevent the creation of new ones. Interrupting existing ones is not great because if you're downloading a 100 gigabyte file and you get 70 gigabytes in and you interrupt it, well, that's like you've just wasted all of that work, right? You'd rather not do that. So we're sort of mostly looking into what we can do for preventing the creation of new connections. This is also work that is ongoing at the moment. It is worth pointing out, though, that actually implementing this has a significantly different set of concerns and trade-offs to the other two forms of rate limiting, right? When we're rate limiting the rate at which users make requests or transfer data, because in our case we're applying those limits on a per second basis, we have a sliding window of here's what you've done this second, here's what you've done last second. 10 seconds ago is like another universe. It doesn't matter, right? Just throw that data away. It's irrelevant. But you could very easily have connections that last a minute or more. And so now suddenly for this specifically, unlike the rest of the system, you care very much about making sure that all the data gets persisted, and that if you have like a failover in your storage medium, that you're not losing anything problematic in there. Similarly, the way that we transfer data involves some UDP packets. If you drop a UDP packet saying this connection got closed, now for all time your 10 connections is now 9 connections. And in the limit you have 0 connections, then your client can't do anything, even though they think that they're not doing anything at all. They can't make a single request. And so there's some different nuances to consider when we're dealing with that. Yes, and as I say, that's an ongoing effort. But we're kind of going down that path, and we'll see where that goes. So finally, let's have a note on some expensive requests. This is a problem that we've encountered rather less frequently than the other two, but it has bitten us once or twice, so we think it's pretty worth considering. You have a client. They're using your object store. They want to download 100 4K objects every second. Obviously, the size of your cluster changes how reasonable the exact numbers are. But downloading objects is a pretty lightweight operation, especially if they're pretty small. This isn't too much of an issue. We go to the storage and we get the data out and we ship it, and that's fine. But recall that our request rate limiting is split by HTTP verb. These are gets. You know what else is a get? Listing the objects in a bucket. Right? This involves a little bit more work, especially if the bucket has many objects. Even more so right? Because you can have buckets with like 1 million objects or whatever, or 100,000 objects. Even more so if those objects all have many versions, right? Because now on the storage, you have to troll through huge amounts of metadata to just find, here is the actual current version of this object in order that we want to now list as the first like 50 objects or whatever in the listing. And so at this point, your index pool probably doesn't want to be friends anymore, right? This is because that's where all of this work has to happen. And this is now for a single GET request, which we were previously considering to be the same as a download. We now have an issue. We have much greater compute on our side for just a single request that's kind of the same from the user's perspective. And this can have broad-ranging consequences. So let's bring up another graph. Here is the latency for creating a bucket for a specific user. This user, at the time, was otherwise not really doing anything else. And yet here we see a significant jump in the time it takes them to just create a bucket. And this is because at the same time, there was another set of users who all decided that they wanted to list all the objects in, well, some of the objects in some very large buckets. And the index pool in particular was struggling to keep up. And so for this user, going back to the original list, this is obviously not a consistent experience, right? This is quite a jump in the graph. And so really what this means is we need to do some extra inspection on requests, right? Like splitting HTTP requests by verb is clearly not sufficient for S3. And so we need to do some sort of deeper inspection. This has been on our to-do list for a while, but of course, because it's only been us once or twice, we haven't really managed to dig into it as much as we would like. This is aided, however, by the fact that for our internal use case, we currently do not support S3 Select. We expect this problem to be much, much worse with S3 Select, where you can just be like, here's 100 gigabytes of data, please return from that data this one number, where we're like summing a column and some CSV data, or whatever the case may be. And so, that's kind of a prerequisite for us to be able to support that. And we have clients that would like to do that, so that's something we're going to have to look into. There are some ideas. We could look at the time it takes for requests to be serviced, or do some inspection and try and forecast this for a given request, how expensive we think it is in some fashion. But we're going to have to do something a little smarter than just this is a GET request. So there we go. That was the three main learnings that we've come out from the last 18 months of things we thought we didn't or hadn't really thought sufficiently hard about. And really the takeaway here is, if you're running something similar, if you're trying to do a similar sort of cluster-wide rate limiting QoS setup, or if you expect to, or if you would like to, then here are some things that maybe you would want to take into account. Either way, please do come chat to me. I would love to talk about this sort of stuff. We do have some hopes of open sourcing the system that we've built when it's ready, when we get the chance. So there may be some opportunity there to contribute back. But for now, this is what we've got. Yeah, and thanks for listening.
Thank you much. Thank you very much, Jacques. Any questions for Jacques?
Thanks for the talk. I just wondered if you could say something more about how you scale the HA proxies. Is it like one per Rados gateway? Or?
Yes. Okay, pretty much. So we just have, on the same host, we'll have the syslog server. I can go back to the diagram if we go way back. The square with this one, the Rados gateway is actually in the square. And so we just have like one each.
Thank you.
Are all the users authenticated, or do you have to deal with anonymous access as well?
So this is, yes. Yeah.
Good
I
answer.
thought you were asking a different question than the one I started answering. We do have some users that have anonymous access. What we do is we have a single usage bucket that all anonymous accesses go into, and this is one of those places where, because they're internal users, we can talk to people and try and help them out, basically. And it's like, well, if the anonymous access usage limit is too low for you, then make an account, do some authenticated requests. Yeah, that's not been a problem for us so far.
This is a quick one. I think in your second slide, you categorized your environments in terms of 4 categories: production, staging, testing, legacy.
Sure.
What is legacy? What's the significance? I'm curious.
But so we have it's an older version of Ceph that was a vendor-provided version, whereas currently we're running on a community release for the newer ones.
Got it.
Okay, that looks like all the questions. Thank you very much, Jacques.